All right, welcome everyone. Welcome back. So you should all be aware that the homework for 5.1 is due this Wednesday by 11:59 p.m. And then assuming that we finish 5.2 in class today, its homework is due 1 week from now, which is Monday, September 7th, 11:59 p.m. So we completed 5.1. We covered everything enough for you to be able to cover the homework. We mentioned one or two things that you shouldn't really have any questions about moving forward, but just further topics of study if you wanted to see them, especially if you're interested in the physics side of things. Today is a very important lecture. If I were going to say that any day's lecture was more important than any others, this would be the one. This is the lecture that if you don't learn it, you can't do anything for the rest of the semester pretty much, because we are going to talk about the 6 primary functions of trigonometry, kind of what they are in relationship to a right triangle. And we're going to go through and study some numbers involving them, some examples, and et cetera, et cetera, et cetera. But we need to start out with just straight up definitions. So what does a right triangle look like as a reminder? A right triangle is one in which there's a 90-degree angle. It's not perfect, but again, it's kind of hard to draw on this tablet, so I do my best. So there's a right triangle. Now, we are using the Greek letter theta. Looks like a 0 with a little curly line through it. Sometimes you'll see me draw it a little straighter than others. It doesn't matter, as long as it's got something to show that it's not 0. So that is theta, that's our angle. So this right here for now is the angle we're interested in. And in relation to that angle, these three sides can be given names. This vertical length over here on the right, we can call the opposite side. This horizontal length on the bottom, we can call the adjacent side. And these names are, what's the word I'm looking for, relevant, because adjacent means the side touching the angle we're interested in. Opposite, this is the side opposite to the angle. So here's your angle, here's the opposite side. So again, the adjacent is the side that touches it, but not this one. You might say, well, isn't this adjacent too? Well, yes, it is technically adjacent as well, but we don't call it adjacent. We call it the hypotenuse. So the slanted side in this position, specifically the one opposite the 90-degree angle. So when you're dealing with a right triangle, the side that is opposite the right angle is what we call the hypotenuse. So opposite, adjacent, and hypotenuse. And you'll see me abbreviate these OPP, ADJ, HYP quite often. Sometimes I'll go single letter O, A, and H. And that's all fine for me as well as for you for note-taking. In my math lab, if they want you to spell out the word, make sure that you're spelling out the word. So we are going to study the 6, yes, count them 6, trig functions. They all relate to those those 3 over there, the opposites, adjacents, and hypotenuses. Can't hit enter, but I can hit tab. There we go. So the first one is sine, S-I-N-E, but we usually abbreviate it as S-I-N. The next one is cosine, which we usually abbreviate as cos. I'm going to tab these so they're a little prettier. Then the next one after that is tangent. Like me, I like to go off on a tangent. Not the same type of tangent, but touch and go kind of idea. That abbreviation is tan. After that, why is that tab so much further than this one? That doesn't make sense. Okay, whatever, doesn't matter. Those 3 are the ones that we're going to use more than the rest. But the other 3 are important and will be used quite frequently. Don't think you can just skip learning these completely. We have our cosecant, which the abbreviation for that is CSC. We have our secant, which its abbreviation is SEC. And then we have our cotangent, which its abbreviation is COT, C-O-T. So those are our 6 trig functions that will be used every day of this course until we get out of trigonometry for things at the end of the semester. And they all are related to the opposite, hypotenuse, and adjacent. In fact, these are all heavily related to each other. A cosecant is related to a sine. A secant is related to a cosine. A tangent is related to sine and cosine. In fact, you can relate cosine and sine. You can relate any of these two together in some way, shape, or form. How are these defined, though? What exactly tells us what the sine is? So a sine tells us to do something with 2 of these 3 things. A cosine tells us to do something with 2 of these 3 things. Every single one of these 6 functions deals with 2 of these 3. So each of these trig functions deals with 2 of the 3 sides. So it might deal with the opposite and hypotenuse. It might deal with the adjacent and the hypotenuse. It might deal with the opposite and the adjacent. How do they deal with them? They're all fractions. They're all ratios of one to another. So those trig functions are just a measure of the ratio of an opposite to a hypotenuse, or an opposite to an adjacent, or an adjacent to a hypotenuse, whatever combinations you can think of, and it's all 6 combinations. So specifically, sine of theta, and I'm going to use my pen now. So we don't just write SIN, we have to put the angle in there. So it'll be SIN, and then there would be a theta next to it. And I want to do this in black, not red. Pardon me there. So the sine of theta. So again, sine is talking about the trig function itself. It tells us what ratio we're going to do, and then of the angle theta. So that tells us this one. There could be another angle up here. We could label this alpha or gamma or whatever other Greek letter we like, which we'll get into later in the semester. But again, we're interested in that ratio from this angle, not this angle, because if we're up here, that changes what we would label as opposite and adjacent. These two would actually swap. So sine is the ratio of specifically opposite to hypotenuse. And I'm going to use the 3-letter abbreviations. Opposite over hypotenuse. Give myself a little more room. Cosine of the angle is the ratio of the adjacent to the hypotenuse. And then tangent of the angle is the ratio of the opposite to adjacent. Those are the 3 most important trigonometric relations we will study all semester, because they are the first brick in the building. They are a building block. They are essential. Without that, you can't do anything else. And these are the 3 of the 6 that we use more often than the others. And I'll go ahead and say why. Because each of these 3 is just the reciprocal of the one it is to the right of. So sine and cosecant, you can find one if you know the other just by flipping it. The same relationship holds between cosine and secant. The same relationship holds between tangent and cotangent. So if sine is the opposite over hypotenuse, that makes the cosecant of the angle the hypotenuse over the opposite. If cosine is the adjacent over the hypotenuse, then secant of the angle is the hypotenuse over the adjacent. And if tangent's opposite over adjacent, that makes cotangent, or cot, of the angle adjacent over the opposite. So again, please note that each one on the right is just the flipping of the one on the left, flipping be reciprocal. Now you'll need to know how they relate. You can't just write sine next to tangent and say tangent's flipping sine. No, that's not the case. It's cosecant is flipping sine. Secant is flipping cosine. Cotangent is flipping tangent. And a lot of people, sorry, I'm coughing, give me a second. A lot of people will think that sine and secant are reciprocals of each other and cosine and cosecant are reciprocals of each other because the s's and the c's. Well, what I would suggest is to actually pay attention to the last one because that one tells the tale. Tangent, cotangent. So the one that is a co of something is the flip. So cosecant is the flip of sine. So sine doesn't have the co, but cosecant does. Cosine has a co, but secant does not. So those are the two flips of each other. Again, one has a co, the other does not. And then tangent and cotangent, one has the co and the other does not. That is the, in my opinion, easiest way to remember which one is a flip of the other. Secant and sine, those words are kind of related to each other. So this is, but you can't say cosine because that's something completely different. And there's a strong relationship between all of these words. But sine, co. Cosine, secant, and don't think that these two flip each other because of that. That's one thing that you could go wrong on. Sine, secant, cosine, secant. Sine, cosecant, cosine, secant. One of these has a secant, one of them has a sine. Tangent and cotangent, both of them still have tangent in them. It's just one has the co, the other does not. Now there is a wonderful abbreviation SOHCAHTOA. This is helpful in the same way that FOIL is helpful for a lot of students, in the same way that PEMDAS is helpful for a lot of students. It's a mnemonic device to help you remember the left three. So I'm going to put a little divider between here, between the left three and the right three. This SOHCAHTOA is helpful for the left three, for sine, cosine, and tangent, because as I said, these are the ones we'll deal with way more often. We'll see them way more often, and most of the time, when we see these other three, we end up just either in our heads or on our pages, turning them into the others to actually understand them. So SOHCAHTOA. This will help us remember the sides and relation sine, cosine, tangent. Sine, let me use the abbreviations, is the opposite over hypotenuse. Cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. Let me just do it this way. That's SOHCAHTOA. S-O-A-C-A-H-T-O-A, and I uppercased all the appropriate letters. So that's so, S-O-H, C-A-H, TOA. Some people like a mnemonic device, kind of like, please excuse my dear Aunt Sally, and what they can do with this is some old horse caught another horse taking oats away. There's another one that I really like to use in a non-recorded class. It's got a little bit more humor to it, and I'm just always a little apprehensive to record things with certain words or phrases, and it's not a cuss word or anything like that, but I just don't want to have in a recorded lecture, and I really dislike that. But it's 2020, I don't want to lose my job over something as ridiculous as a funner version of this. So that's the one you're going to get. If we had me in person, it'd be another one because then nobody could prove I said it right. Haha. And even that's probably, that's definitely not true, but I just felt more okay with it. So maybe go to the internet and just look up more fun phrases that can go with SOHCAHTOA, and it's probably easy to find as well as maybe one or two others. But that's the one you're going to get from me, whether I like it or not. Some old horse caught another horse, taking oats away. I'll even give you some hints as to what it was. Instead of horse, it was hippie. And instead of taking, it was tripping. And I'm sure he or she was not just falling over, but again, I didn't say anything besides that. Some old horse caught another horse, taking oats away. SOHCAHTOA. I think SOHCAHTOA, as long as you know the letters of them, you're not thinking it's SOCATOA. As long as you know it's 3 letters for each one, I think that that's perfectly fine. So, SOH, that says that sine is the opposite over the adjacent. Oops, I don't want blue, I want black. So if here's our angle, and we wanted to know that the sine of theta, it would be its opposite over the hypotenuse. It would be its opposite over its hypotenuse. That's how we can use that. Or if we wanted the cosine of theta, I'm only labeling the ones that are relevant this time. If we wanted the cosine of theta, and again, these have to be right angles here. Well, cosine is the adjacent over the hypotenuse. It's a terrible looking J, but it's a J. So adjacent is not that one. I'm sorry, I'm looking at the wrong thing. ADJ over the hypotenuse. So it would be this number over that number. You'd have numbers there. And then if you wanted tangent, that uses the opposite and adjacent. You're just looking for 2 numbers on a triangle and dividing them in a specific order. That's it. You need to embed this in your brain. You do not get to forget this ever this semester. If this was an in-person class, I could just randomly quiz 1 or 10 students on this and say, SOHCAHTOA, what's cosine? And they should know it instantly. In fact, for my in-person classes, I usually give a quiz on this the next day after we teach it. I'm not going to do that with the scenario we're in right now, but just note that it's equally as important. You need to pretend that we have a quiz on this Wednesday and have this memorized by then, because remember, when we go on to 1.5, you probably need to know 1.4 to understand it. This is the first building block of really doing trigonometry. Yeah, we learned how to convert between radians and degrees last time, but that's not really a trig problem that I'm going to be testing on, as I've mentioned. That's just part of, hey, if I give you something in radians and it's not understandable to you because you like degrees, then you can convert it to degrees. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. Let's try it out. Example 1. Evaluate the 6 trig functions given the following triangle. A, and I'm going to put our angle right here. I don't have to do the angle here. We will very often put the angle up here. You'll have a homework problem with the angles up here. And you have to remember that the opposite and the adjacent, the opposite would now be the bottom and the adjacent would be this vertical side instead. Because we're always thinking opposite in terms of the angle we're considering. And the sides lengths are going to be 3, 4, and 5. This is a very cool right triangle because all 3 of these are integers or whole numbers. You don't get that very often in right triangles. There's only a couple of right triangles as a basis where that's true. Most of them have a radical somewhere in at least one spot, as we will see moving forward. All right, so we're going to do the sine of theta. We're going to do the cosine of theta. We're going to do the tangent of theta. Then we're going to do the cosecant of theta, secant of theta, and the cotangent of theta. Now again, all we're doing here, we have these sides labeled. First of all, moving forward, you generally don't get all three sides labeled. Only two will be labeled, and you'll have to find the third side using something known as the Pythagorean Theorem, which you've probably heard of, you've probably used, but we'll remind you of soon. So all I'm looking to make is a fraction involving two of these three numbers. That's all these trig functions are as a basis. It's a ratio of one side's length to another side's length. But that ratio gives us a whole bunch of things that we can use moving forward. All right, so sine. So, S-O-H, S-O-H, so in SOHCAHTOA. Opposite over hypotenuse. So in terms of this triangle with our angle here, that makes the opposite the 4 and the hypotenuse the 5. See, if our angle was up here, the opposite would be 3, because then that would be opposite. So opposite is 4. The hypotenuse is always the side opposite the 90-degree angle. So that's the 5. So our answer is 4/5. That's it. That's the entire 1/6 of the problem. Nothing crazy. The cosine of this angle, so that's ca, C-A-H. Cosine is adjacent over hypotenuse. Adjacent meaning the side that it touches, not the hypotenuse, and then hypotenuse is the opposite of the 90 angle. So 3 is our adjacent, 5 is our hypotenuse, and you got to get the order right. It's not 5 over 3, it's 3 over 5. Tangent, TOA. Now again, you don't get an abbreviation for cosecant, secant, and cotangent. Nobody's really come up with a clever mnemonic device for it. And plus, with the whole reciprocal relationship that I will actually write down formally later, it's just really easy to find these three based on the other three, but we'll get there. Tangent is TOA, opposite over adjacent. So again, here's our angle. Opposite was 4, adjacent was 3. There's nothing insane about this. It's just understanding which one you label opposite, which one you label adjacent, and memorizing a few little details. So opposite 4, adjacent 3. So there are our first three, 4/5, 3/5, and 4/3. Cosecant, secant, and cotangent. These are, again, the basic idea is the reciprocal of these, but let's actually go to the standard definitions for now. Cosecant is the hypotenuse over the opposite. Maybe for these first couple, you even want to label these. Maybe you want to label the 3 as the adjacent. Maybe you want to label the 4 as the opposite. Maybe you want to label the 5 as the hypotenuse. You're more than welcome to do that. So we want cosecant, which we said was hypotenuse over opposite. C-H-O, it's, show, maybe, I guess, C-H-O, like using the C with an S sound. Show, S-H-A, show, sha, co, C-A-O. I mean, I can't even, every semester I try and get to that without laughing, but I gotta laugh. Show, sha, cow. Okay, so cosecant. That's the hypotenuse over the opposite. Hypotenuse over opposite, 5 over 4. And I'm doing these in red for a reason. Secant. If you go back up here, secant was the hypotenuse over the adjacent. Hypotenuse over adjacent, the sha. Hypotenuse was still the 5, the adjacent is still a 3, so that's 5/3. And then cotangent, if you go back up, is adjacent over opposite. Adjacent over opposite. Adjacent's 3, opposite's 4. 3/4. That's it. That's the entirety of example 1A. Notice the reds are the blues, but flipped. 4/5 flipped is 5/4. 3/5 flipped is 5/3. 4/3 flipped is 3/4. Now, there's, again, an association here. I can't just put the cotangent next to the sine and say that that's the flip of that. 4/5 is not flipping 3/4. It's these two are directly linked together in terms of a flipping. These two are linked in terms of a flipping, and these two are linked in terms of a flipping. If you write them in a wrong order and try and use the flipping in that manner, you're going to make mistakes. And again, that's something that I will label after one more example. Yes, one more example. B. I want it in black. Back in black. All right, so this triangle, and I will admit the 3, 4, 5 triangle, while it's awesome that they're all whole numbers, we really aren't going to use this triangle too often in this class. In that admission, I will also admit this triangle, which has opposites and adjacents no matter where you are, being 1 and 1, so they're the same length, has a hypotenuse that is the square root of 2. I will at some point actually prove that this is the case. And we're going to keep our angle here, but because the opposite and the adjacent are identical, you could actually put the angle here and it would not change anything. Kind of cool, if you ask me. But my definition of cool is, well, weird sometimes. So again, let's find the sine of the angle, the cosine of the angle, the tangent of the angle. Notice I don't get to skip writing this. If I just write CSC, SEC, and COT equals, this is bad form because what's the variable? What's the angle? What's the x? Remember, theta is basically our x for trigonometry in a lot of cases. So which angle do you mean? Do you mean this angle or do you mean this one? Or do you maybe mean the right angle? Because you could still somehow at some point talk about sines, cosines, tangents, cosecants, secants, and etc. from a right angle position instead. We're not there today though. Okay, so theta, theta, theta. Sometimes my thetas look like 2s. Please forgive me. I was not graced with amazing handwriting. I'm left-handed, so there you go. There's my problem. All right, blue for the first 3. SOHCAHTOA, SOHCAHTOA, S-O-A. Remember, you can label them if you like to. I'm going to try and avoid it this time, though. It's pretty much labeled above, though. This one is the opposite. This one is the adjacent. So, S-O-H, opposite over hypotenuse. The opposite is the 1 over the hypotenuse's square root of 2. I did not leave myself enough room here. I just need to move these to the right a little bit. You know what? That's not going to work. I'm just going to start fresh. I just want to rewrite those a little further to the right because I need to simplify that 1 over square root of 2 in a second. So this is cosecant. This should be enough room. And then cotangent. So 1 over square root of 2, because this was the 1 and this was the square root of 2. Opposite over hypotenuse. This right here is a terrible format for an answer. Terrible format for an answer. You never in this course, unless it's an extreme situation and I mention it, you can never leave an answer as 1 over square root of 2. It's this that's the issue. You can't have square roots in the bottom. You should have learned that in pre-calc. You should have learned that before pre-calc. You should have learned that in like an Algebra 2 class, in fact. So you have to do what's called rationalize the denominator. And I'm going to make a memo about this after the example is done, but you have to do what's called rationalize the denominator. What we do is we multiply top and bottom by what the bottom is for this case, because there's no pluses or minuses. This is an easier case. You're just going to multiply top and bottom by the square root of 2. So if your bottom is square root of 2, square root of 5, square root of 13, this is the technique. Multiply top and bottom by the square root that's in the bottom. what that's going to do for us, my blue back. The top, 1 times square root of 2 is a square root of 2. In the bottom, square root of 2 times square root of 2, since they're both inside, makes the square root of 4. But we know what the square root of 4 is. It's 2. So the answer is the square root of 2 over 2. A little more room. So this right here is called rationalizing a denominator. When you have a monomial, just one term in the bottom, a square root of 2, square root of 5, and we will see this literally hundreds of times in this course. So if this is rusty, derust. Multiply top and bottom by the square root that's in the bottom, and that will get rid of the square root because we cannot have square roots in denominators of answers. It's okay in the top, but not the bottom. And it's funny because this answer looks uglier than the original problem. And yes, it does look uglier, but there are things we can do in this format that we couldn't do or recognize in the original format. So this is very important, and it might look silly. You might think it looks worse, but again, in terms of math, it is better, it is simpler, it is more functional. So let's try out the cosine. 1 over square root of 2 was the sine initially, because that was the opposite and that was the hypotenuse. Well, cosine is ca, C-A-H, adjacent over hypotenuse. Adjacent's the one that touches the angle, so this is the adjacent. It's still a 1, but it's the different one. So that's 1 over. Hypotenuse, still square root of 2. Again, these ones at the top are different. The sine one was this one, whereas the cosine's one was this one. It's just coincidence. But also coincidence, we can't have a square root in the bottom, so we gotta multiply top and bottom by square root of 2. That'll give us the same thing, ultimately giving us square root of 2 over 4. Same middleman work, I'm not gonna reinvent the wheel. For the tangent, TOA, T-O-A. Let me write that one last time. S-O-H, C-A-H. T-O-A. You'll see me write that in class for the next month or two, probably. So TOA, T-O-A, opposite over adjacent. This is the opposite one. This is the adjacent one. So it goes 1 over 1, which 1 divided by 1 is 1. Much simpler, that one. Okay, well, what about these other three? I didn't leave as much room for them, interestingly enough. Do you think maybe I've got to do this again? Maybe not, maybe not, maybe not. Let's see what happens. So let's make my orange red again. So cosecant, remember, this is going to be hypotenuse over opposite. And if you are rusty, not rusty, if you haven't learned that yet, go back to where you read it. You wrote it. Read it 50 times, write it 50 times, use it 50 times, whatever you have to do to learn this stuff. Cosecant is hypotenuse over opposite. Hypotenuse was the square root of 2. The opposite is this one right here. So square root of 2 over 1. But we can have square roots in the top. But 1 in the bottom means we don't need the bottom. So that's just square root of 2. Now you might say, well, Mr. Beckner, that doesn't look like you took the previous one and flipped its answer. You kept saying that. Well, actually, if you flip the initial thing before you did all this cleaning up for its particular problem, if you flipped 1 over square root of 2, you'd get square root of 2 over 1, which is square root of 2. If you flipped this version, the answer, you would have to go through and do this orange step again. And believe it or not, by the end of it, you would get the same answer, but I'm not going to do it that way. Secant. So cosecant was the hypotenuse over the opposite. Secant is the hypotenuse over the adjacent. Hypotenuse over adjacent. The hypotenuse being the square root of 2. The adjacent being this one. Still a 1, but it's the bottom one. And square root of 2 over 1 is once again square root of 2. Time I say once again today, I got Bernie Sanders in my head. Once again, I am asking you to do trigonometry. Cotangent. So TOA that was opposite over adjacent. Cotangent's adjacent over opposite. Adjacent 1, opposite 1. That 1 over 1 is still a 1. I will put less of an emphasis on these later 3 trig functions versus the first 3 in the memorization of opposites, hypotenuses, and adjacents. I will even be completely honest with you. I don't have them memorized in my brain that way. You know why I don't have them memorized in my brain that way? Because I know that cosecant and sine, I can get the sine and flip it. That's easier than memorizing a whole new set of opposites, hypotenuses, and adjacents, especially if they don't have a helpful mnemonic device like SOHCAHTOA. So again, you can certainly do them this way. You can do them that way all semester. As I said, myself, and I emphasize that learning can be done from multiple angles, from multiple methods. I'm not the math teacher that says, do it my way or you get an F. Never have, never will. I'm the teacher that says, if you have a method that always works, use that method. Who cares how you get the job done? As long as it's legal. Okay. So, what are those relationships, those reciprocal relationships? Here we go. It always takes me 1 or 2 times to spell that correctly. Reciprocal relationships. It's that cosecant of an angle is 1 over sine of the angle. It is that secant of an angle is 1 over cosine of an angle, of the same angle, of course. And that cotangent is 1 over tangent of the same angle. These are the reciprocal relationships. Saying 1 over means flip it. You don't have to do it as a 1 over. If it's originally a fraction, then you just flip the fraction. I hope everyone knows what a reciprocal is at this level. Flip the fraction, or take 1 over it if it was a whole number. Then what we also have are our relationships between tangent and cotangent versus sine and cosine. I don't want to use a slash for that. Tan and or cotan relationships, relations to sine and or cosine. So tangent of theta is the sine of theta over the cosine of theta. I haven't said that one yet, but it's true, and I will show you why. The cotangent of theta, if you understand the idea of reciprocals, if tangent is this, cotangent is a reciprocal of tangent, then just flip the sine and cosine. It should be cosine of theta over sine of theta. Now, this is not a very heavy-handed proofs class, but I will prove some things. I will prove some things. I will prove the tangent relationship. So let's take the tangent of theta is supposed to be sine of theta over cosine of theta. But here, on this step, let's replace with opposites, adjacents, and hypotenuses. So at this step, so after the equals, you will no longer see the word sine and cosine, you'll see words like opposites, adjacents, and hypotenuses. Hypotenae, the plural of hypotenuse. Not that anyone cares. So sine of theta, that was so, S-O-H. Sine is opposite over hypotenuse. So the sine of theta is opposite over hypotenuse. So the top fraction, the top of this fraction is going to be a new fraction. It's the opposite over the hypotenuse. And in fact, let me do the bottom in orange. Oops, that's not what I wanted. Let's do cosine of theta. Drop. Thank you. There we go. Colors are always helpful for proofs. So sine, the red, was opposite over hypotenuse. So there's the top of the fraction. Here's the black division. Here's the black division. Now the cosine of theta, that's ca, C-A-H. Cosine is adjacent over hypotenuse. So A, D, J over H, Y, P. Now, this is a fraction divided by a fraction. This is not the only time this semester that you'll see this. This should not be the first time you have ever seen this. You should have been taught how to handle fractions on top of other fractions, also known as a compound or complex fraction, depending on your teacher and textbook that you've used. As long as there's no pluses or minuses mixed up in this, like another fraction is being added in the top or subtracted in the bottom, you can just turn this black fraction bar into the old school division bar. So with red, let's put red here. So the red, the opposite over the hypotenuse. And instead of the black ink being a division bar as a fraction, let's make it the division symbol. And then we have our orange ink, adjacent divided by hypotenuse. The only thing I've changed was I turned this right here into this. Fractions are divisions. But how do we divide fractions? We multiply by reciprocals. So we don't change the red. The first one does not change. And if this is something that you don't remember or are rusty with, guess what I'm going to say? You got to practice, 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 because I already said it's going to be seen all semester long. With the orange, we flip hypotenuse over adjacent. And then what we can do here is cancel. There's a hypotenuse in the bottom, there's a hypotenuse in the top, so we can cancel those. And for the interest of my future notes, I'm just going to rewrite it. So equals down here, OPP over HYP times HYP over ADJ. The hypotenuses, the hypotenuses, whatever you want to say, they cancel. So we end up with opposite over adjacent. So after simplifying this, we get down to opposite over adjacent. Opposite over adjacent, why does that sound familiar? Go back to your definitions. Opposite over adjacent, which one of these is it? Opposite over adjacent, right here. Tangent is the opposite over adjacent. So this is equal to tangent of theta. That is the same thing as this, so that is a proof. You will see a fancy abbreviation from me sometimes for proofs, QED. It's Latin, quod erat demonstratum, and I'm not going to spell that out because I'd have to look it up first. Quod erat demonstratum. It means quite literally that which was to be demonstrated has been. It means proofed. It means done. So a lot of people like to say QED when they're done with proofs because they feel like it makes them sound fancier, and it makes them sound like, well, even if I got a mistake in here, since I said QED, the teacher's going to think I did it right. Trust me, I know better. Most of your math teachers know better. I said most, not all. Exceptions to every rule, right? All right, how are we on time? Halfway there, halfway there. Okay. So the proof of the cotangent relationship is quite literally the exact same as here, except the orange and the reds are all upside down from each other. The orange would be before the red here. The hypotenuse would still cancel, and you'd end up with orange over red here, which would be the cotangent. It would have been adjacent over opposite. You can see similar proofs done for these three relationships as well, but I think it's pretty easy just to see based on appearances. If you look at sine, if you flip these two things, you get cosecant. So that proves, good enough, right? That cosecant is flip sine. The same relationship holds between secant and cosine, the same between cotangent and tangent. You don't have to write the left version as the left and the right as the right. I can write that sine is equal to 1 over cosecant. I can write that cosine is equal to 1 over secant. I can write that tangent is equal to 1 over cotangent. All of those are perfectly fine because they're reciprocals of each other no matter what the format is. It's like two sides of a coin. If you flip a coin once and then flip it again, you're back at the original. So you can say heads is flipping tails, or you can say tails is flipping heads. And when I say flip, I mean once, not to flip it with your thumb in the air many times. I mean literally to just change from one side to the other. A looser definition of flip, if you will. And then I won't say last important theorem, but the last one from this section for now, to go with these, is the Pythagorean Theorem. I mean, this is just all over the media, not just in your actual math class. It's if you've got a right triangle, no matter how you draw your right triangle, this is just the classic way I like to do it. The things that we've been calling opposite and adjacent, so this would be opposite and the bottom would be the adjacent, those are known as legs. So legs are attached to the right angle. The hypotenuse is not a leg. So you'll hear me, not see me, because you don't see me literally, but you'll hear me say that phrase semi-frequently throughout the semester. Instead of calling these hypotenuse, opposite, and adjacent, let's give them letters because that's how the Pythagorean theorem is done. Let's call the legs A and B. These are completely interchangeable. I can swap A and B. It doesn't matter because the Pythagorean theorem doesn't actually have anything to do with this angle theta. And then the hypotenuse we traditionally call C. And the Pythagorean theorem states that the sum of the squares of the legs is equal to the square of the hypotenuse, the side opposite the right angle. And you'll see movies and TV that like to say that a lot fancier and more wordy, I suppose. But it's just a squared plus b squared equals c squared. We're not going to prove this. There are tons of proofs. My favorite always being the geometric version where you actually draw out a square of length A on the bottom, a square of length B to the right of it, and then a square at an angle of length C. And basically you geometrically rearrange the shapes so that the two squares below and to the right end up fitting in the square where C is. If you don't memorize this theorem, you're going to have as much of a difficult time throughout this course if you don't memorize SOHCAHTOA and the actual relationship between sine, opposites, adjacents, hypotenuse, cosines, tangents, all that stuff. We will use this constantly throughout the semester because I traditionally do not give you all three sides of a triangle. Going back to these two previous examples, I normally wouldn't have given you maybe the 5 here or maybe the 1 here. Or maybe I don't give you the 4 and I give you the 3 and the 5. Because we can always use this and its algebraic rearrangements to find the other side. So some variations to this. And I'm not asking you to memorize these, but it would be that C is equal to the square root of A squared plus B squared. Or you could say that A is equal to the square root of C squared minus B squared, or that B is the square root of C squared minus A squared. This is just an algebraic rearrangement of those three things and solving for the other. Now you might say, all right, well, you took a square root. Why didn't you do a plus or minus square root? Because usually when you take square roots, you plus or minus them in an algebra sense. Notice I said in an algebra sense. These always relate to geometry. We can't have negative links in geometry. So how could A be a negative square root of something? That would make it negative, which doesn't make sense. That's why we don't worry about the plus or minus square roots here. In fact, a lot of the time in this course, that super important plus or minus aspect from pre-calc 1 won't be an issue in here. I'm not saying it's never an issue. I said usually. Now, if you're going on to calculus, that issue will come back so you don't get to forget it. That's the thing about math. Most of the things you learn, you usually end up reusing in a later course. I did say most, I did not say all. So with that in mind, let's try out example 2. Find the missing side. And we'll have a right triangle with our angle being here like I prefer generally. And we're going to have sides of 1 and square root of 3. So we'll call this C since it's the unknown and it's on the hypotenuse. Now, I did not ask for the 6 trig functions this time. I just asked for the missing side. This is just to demonstrate Pythagorean. So the a squared plus b squared equals c squared. The a would be, you could call the 1 or the square root of 3, just as long as the b is the other one. So if you want to label those, let me make this blue again. You'd say, I'm going to choose to say a is 1 and b is the square root of 3. So using that formula, and again, I'm going to always start with the black one. Some students will memorize these rearrangements, but me personally, I just always do the rearrangement as I go. So plugging those two in that equation, c is unknown. So we get, let me see this. We'll get 1 squared plus the square root of 3 squared equals c squared. A squared plus b squared equals c squared. 1 squared is 1. Square roots and squares in this form cancel as long as there's no pluses or minuses inside without parentheses. So that's a 3. And then that's c squared. 1 plus 3 is 4, so we get 4 is equal to c squared. Then you need to take not a plus or minus square root, just a square root. No plus or minus is necessary, again, because this is geometry. You can't have negative distances. You can have negative angles, but not negative distances. So the square root of 4 equals the square root of c squared. The reason we did that is because square roots and squares cancel. And we get 2 is equal to c, and that's our answer. This is one of the 2 most common triangles we will study throughout this course. This is known as the 1, 2 square root of 3 triangle, also known as the 30, 60, 90 triangle, as we'll come to see in passing sooner than later. The other one that we primarily use is this 1, 1 square root of 2 triangle, also known as the 45, 45, 90 triangle, as we'll come to see in passing. So that's how we can find a missing hypotenuse. If I give you the legs, again, the a and the b won't matter because they would just swap the position of the 1 and the 3 here. The order of addition doesn't actually matter. B, let's draw it to the right instead, just to change up one tiny little thing. Here's our angle, not that the angle will matter. I'm going to choose to label this as A, then this will be 6, and then this will be 9. So this is an A, whoops, that was weird. This is an A on the left, this is a 9 on the hypotenuse. If you wanted to call this a B, nobody's going to care ultimately, but I chose to call it an A. So the A is A. That makes the B 6 and the C 9. So plugging those into Pythagorean, which was right here. A squared plus B squared equals C squared. So we go A squared, because A is A, plus B squared, which is 6 squared, not plus, equals 9 squared. 6 squared is 36, 9 squared is 81. You better be able to do that without a calculator. And this is just an algebraic equation to solve. So we subtract 36 on both sides. Like I said, I'm not actually using these variations. That's just ultimately what it ends up boiling down to. So we get A squared is equal to 81 minus 36, which is, what's that, 45? Then we take the square root. So the square root of A squared equals the square root of 45. I'm going to need some more room, so let me just go over here from there. The square root of A squared is A. The square root of 45 we do not know, but we will not stop here, because 45 can be broken up. Remember, in pre-calc and in Algebra 2, you should have learned that if you can simplify these, you have to. Even though I can't take the square root of 45, I can write 45 as a product of 2 numbers, and the goal is so that one of these numbers you know the square root of. Specifically 9, I know the square root of, so 9 times 5. You might say, well, why not do 3 times 15? Because I don't know the square root of 3 and I don't know the square root of 15, so it doesn't help. The square root of 9 you can pop out. It's 3. So we get 3 square root of 5, and that's as far as we can take it. I know it looks more complicated than square root of 45, but same thing as I mentioned earlier with the radicals and bottoms. This is technically a simpler answer, and we can do things with 3 square root of 5 that we can't do with square root of 45. Not in regard to this problem, but in the bigger picture. There we go, time, 18 minutes. Cool. So that's how we can find a missing side, whether it's the hypotenuse or it's one of the two legs. And it never matters which the two legs you're looking for, and it never matters what variable you call the other one. I could have called them x in both instances, but I just tend to call hypotenuse C and a leg either A or B personally. All right. So we mentioned the Pythagorean theorem was a squared plus b squared equals c squared. From the Pythagorean theorem, we can get 3 Pythagorean identities. So this is from, and again, the Pythagorean theorem, I'll put above it, was the a squared plus b squared equals c squared. Now, if you instead of writing a, b, and c, if you wrote opposites, adjacents, and hypotenuses, where they were appropriately supposed to be, then you can play around with this thing by dividing a bunch of stuff, and you end up getting these 3 things that I'm about to show you. You get that sine squared of theta plus cosine squared of theta is equal to 1. So that's the first Pythagorean identity. We get that tangent squared of theta plus 1 is equal to secant squared of theta. That's the second variation. And the third variation is 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. So all 3 of these can be established by, instead of writing A, B, and C, by writing opposite, adjacent, and hypotenuse, and then dividing by either opposite squared, hypotenuse squared, or adjacent squared, and just all these little tricks and tweaks. I'm not going to do the proof of going from the Pythagorean theorem to these 3 identities, but what I will show you is the basics of it, how we can actually take this first one and turn it into the second and third, because you must have these memorized. Asterisk, asterisk, asterisk. The second and third versions can be easily found from the first. So again, I'm going to tell you, I'm going to be completely honest about myself and the way I learn. I'm not great at just straight up memorization of facts. It's not my forte. I'm more about connecting dots, finding a logical flow, an A to a B to a C kind of deal. I can memorize some things, but then if I can find other things without just flat memorizing them, that's the way I like to do things. Do I tell you how to do things? No, I give you suggestions. So one student, Bob, maybe Bob memorizes these 3 outright, but then another student, Jane, only memorizes the first one, and she uses the trick I'm about to show you to get the second or the third when needed. Because, once again, sine, cosine, and tangent are the ones that we see most often, the ones that we like to deal with most often because they're simpler, and it's just for consistency. Even more so, sine and cosine we can stick to most of the time. So this first version is going to be seen probably 5 to 10 more times frequently than the second and third versions. So that's why I memorize the first one, and then just under the rarer chances the second or third pop up, I can do this proof, if you will, I'm about to show you. So here's the basic idea. Start with the first, then divide all terms by either sine squared of the angle or cosine squared of the angle. It's kind of what I was saying that you can do with this to turn into the others. So start with the first one. By first, I mean sine squared plus cosine squared equals 1. This one's pretty easy to remember. And again, you'll see it over and over and over and over and over. These are a little more awkward with the mixing of tan and a secant or cotangent and a cosecant. At least these two have the cos together. At least these two don't. But it might be easy for you to put the cotangent on the wrong side or the secant on the wrong side. So let's start with the first one. Sine squared theta plus cosine squared theta equals 1. So what I'm going to do is, and I said by either, not both, either, one or the other. Let's do the sine squared first. Is that going to end up giving us the second or the third one? I know, but you don't yet. Let's see which it is. So we're just going to divide all terms. Whatever we do to one side, do to the other. So we're not breaking any algebra rules. We're going to divide everything by cosine. I'm sorry, I said by sine squared, didn't I? So let's do the order I said. Divide all terms by sine squared. Now, why are we doing this? Because look what happens. We can cancel. Sine squared, this sine squared with this sine squared. Anything divided by itself is 1. So this is now just 1 here plus. Now, this middle term, cosine squared over sine squared. Let's go back and look at those tangent cotangent definitions, which were right here. Cotangent is cosine over sine, tangent is sine over cosine. So if we saw a relation of cosine over sine, we could instead write cotangent if we wanted. But what about those pesky squares? Well, it's the same thing on top of the same thing, both being squared. So that's just cotangent squared. So we're canceling, and we're using trig identities. Trig identities, trig idents, that's what that says. Cosine over sine is cotangent, so if they're both being squared, it's cotangent squared. Equals 1 over sine squared. Well, 1 over sine, sine we said was the reciprocal of cosecant. So instead of writing 1 over sine, if we don't want to write it as a fraction, we can instead write cosecant. But since it's sine squared, this is cosecant squared. So look at this. Just doing one simple algebraic step, we were able to get the third of the 3 identities. That was not anything super crazy complex, but you do have to remember how to establish it. So again, Jane, I said, would memorize this one and use this quick little algebra trick to find the other 2. If you're not Jane, if you're not going to remember this trick, you got to flat out memorize these 3, because that's the only trick I know off the top of my head to get to the second and third. Again, there are other ways. You can go straight from the a squared, b squared, and c squared to get to these, but it's the same exact concept as what we're doing here. It doesn't make it any easier. Okay, so how about if we again start with the sine squared plus cosine squared equals 1. I don't always say the angle out loud, but I do write it. And again, if you ever see those looking like 2's, they're not 2's, just poor handwriting from your teacher. This time, instead of dividing everything by sine squared, let's divide by, you guessed it, cosine squared of the angle. Not just the left side, not just the things that have trig functions. Whatever you do to the left, you got to do to the right. And then we cancel and use our trig identities. So this time the cosine squared plus cosine squared is going to cancel. So that's a plus 1. This right here is the plus 1. I'm skipping the first term just for a second. I brought down my equals. How about this sine squared over cosine squared? When we had cosine squared over sine squared, that was cotangent squared. If you remember from earlier, sine over cosine is tangent. With that being squared, that just makes this a tangent squared. and then equals 1 over cosine squared. Well, 1 over cosine, we said earlier, 1 over cosine was secant. So we can write that without a fraction. Well, if that's squared, that just makes this secant squared. And there we are. There's the second one, tan squared plus 1. Because when you were writing the second and third, you might have been wondering, why on this one did they write the 1 second, and then on this one did they write it first? Well, you don't have to because of the properties of addition. You can certainly write 1 plus tangent squared, or you could certainly write cotangent squared plus 1. The reason I write them in that order is because, now admittedly, I do have them memorized, but the memorization in my head is completely based on the tactic I just showed you. So in that tactic, it's very natural for the tangent squared to become the first term, and it's very natural for the cotangent squared to become the second term. So that's why in my head the formulas are done this way. But you could certainly find a textbook where these two terms might be swapped, or these two terms might be swapped. But the secant squared has to be by itself, the cosecant squared has to be by itself in these forms. The first one especially, we'll see algebraic rearrangements of it constantly throughout the course. We're going to move the cosine squared over or move the sine squared over. So be prepared for that. So again, you have to memorize all three of these, or at least memorize one and be able to get the other two via a tactic that your teacher has taught you. And in my opinion, it's a simple tactic, but if you don't like it, memorize all three. If you're only going to memorize one, memorize the first, but you won't be making an A on the test. You might get a B. But if you don't memorize the first, you're probably looking at like a C. Because again, the first is used way more often, at least by design. All right, what do we got? 5 minutes. Let's go ahead and write the definition for cofunctions down. I don't think we'll get to examples, so don't want to waste time. Cofunctions. And I want to kind of point out that this is not the same as like sine versus cosecant. Those weren't cofunctions. It's just that cosecant has a co in front of the word secant to let you know it's the reciprocal of sine. Cofunctions work a little differently. This has to do with the fact that the two angles of a right triangle add to 90 degrees. The two, let me be more specific, non-right angles and I'll explain after I type these up. But the sine of theta is the same thing as doing the cosine of 90 degrees minus theta, or pi over 2 minus theta. The tangent of theta is the same thing as doing the cotangent of 90 degrees minus theta. And the secant of theta is the same thing as doing, you might be able to guess it, the cosecant of 90 degrees minus theta. Now these work the same way as reciprocal functions. You can write them out two different ways. I didn't do that for the reciprocals, but I will for these. So the other version is that the cosine of theta is equal to the, why did I start with the parentheses? Sine of 90 degrees minus theta. Notice the 90s come first. That is very important. The cotangent of an angle of theta is the tangent of 90 minus the angle, 90 degrees minus the angle, or pi over 2 minus the angle. And the cosecant of an angle is the same as the secant of 90 degrees minus the angle. That was a really ugly theta there. There we go. I gave you a couple quick definitions last class, and they were complementary and supplementary angles. The word complementary starts with CO, cofunctions. So these are complementary functions, complementary angles. Remember, complementary angles add to 90. It's like having two angles in a right triangle where we're not dealing with the right angle. So this works because this basic idea. I don't want blue, I want red. If this is a right triangle, if I call this angle, let's go with angle, I don't want to call them angle A and B. Let's just call this one theta, just to keep it appropriate. Let's pretend this angle for a second was 1 degree though. If this was 1 degree, so this is an if game, if this was 1, this would have to be 89 in degrees. I'm just skipping right at the writing the symbol, because they have to add to 90. If this was 2, this would have to be 88 so that they add to 90. If this was 10 degrees, this would have to be 80 degrees so that they add to 90. But I don't just have to pull that 80 out of my head. I can say that this angle right here is 90 minus 10, which is 80. That's the relationship between the two non-right angles of a right triangle. If you know one of them, you can find the other by doing 90 minus the first. So if the first angle is theta, the second angle has to be 90 degrees. I drew that triangle too small. There we go. If this is theta, this has to be 90. I'm still doing that as a bad setup. 90 degrees minus theta. That's that angle. I could swap them. If I call this angle theta, then that makes this one 90 degrees minus theta. I might understand so far, but then why does this work? Well, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. When you change the angle, opposites and adjacents change. So the opposite of theta, this is the opposite of 90 minus theta, but the opposite of theta is also the adjacent of 90 degrees minus theta. So the sine of one is the cosine of the other. You just changed the concept of opposites and adjacents. So the opposite of 90 minus theta would be the adjacent of theta. So this is going to give us a strength if maybe the math or the information we're given is up here, but we'd rather perceive it from here. So if we know this angle is, say, 42 degrees, we can just say, hey, let's deal with the 47 degree angle instead, because I'd rather deal with its sine instead of the cosine of this one up here. So that's the strength. That does not conclude 7.2. We will be doing more material next class, so that means that you do have a little more time with the homework, but honestly, we've covered 85–90% of the material, so it is my suggestion to go ahead and try and get as far as you can in the homework for 5.2. And I did label this section as 5.2 at the beginning, right? Yes, I did. So again, we have not finished this yet, but we have done almost everything. We'll probably finish this in the next 10 to 15 minutes of class on Wednesday. Besides that, if you don't have any questions, let's see, do we have to submit any work for the homework? So someone asked me that in email and I responded. I don't remember if that was you or not, but for everyone else, just in case, no, I do not need to see your work for homework, only for tests. That's the only time I will require you to submit work to me. If you have a homework question that you need to email to me, it would probably benefit you to show me work and to send that in the email. But again, not a requirement, and that's only for assistance. So I hope I cleared that up. Besides that, that's it for our class today. Have a good one. Get to studying this stuff, get to practicing this stuff, get to memorizing this stuff, and we'll see you on Wednesday. Take care.